Krishna, and welcome to this month's webinar. Thank you all for attending. Let's see, before we get started, just a few quick bookkeeping items. The presentation will begin shortly and go on till approximately 1 p.m. As in prior sessions, Kyung has agreed to stay on for a bit after 1 to address any questions that people may have. The slides and the recordings will be available at the end of the session. Log into your Malibu account to view them. And please keep your telephone or microphone muted at all times. Only unmute yourself to ask questions. If you have dialed into the conference by phone, you must have entered the audio pin. This should be there either in the email that you got or on the screen in front of you. I can only unmute you if you do so. Of course, if you dialed in by VoIP, then there is no problem. You should be able to just unmute yourself to ask a question. For those of you who prefer to ask questions by instant message, there's a chat window. Please ask your question there. Kyung has indicated that he welcomes dialogue and questions. He does have a lot of material, so at his discretion, your question may be deferred to a logical point or to the end. So please do keep the session interactive. Ask questions as you have them. Anyway, with that, let's get started. Today, we are delighted to have Kyung Lee talk to us about autonomic thermal management in data centers. As you all know, data centers and power management has become a huge focus for the computing industry, especially as we move to the cloud. So Kyung joined in 2009 as a PhD student in the Department of Electrical and Computer Engineering at Rutgers University. He currently is under the guidance of Professor Dario Pompili and is a member of the Cyber Physical Systems Lab and is conducting research supported by the Center for Autonomic Computing, CAC, which is an NSF-funded research center. Previously, he worked on integrating wireless sensor networks in MATLAB at MathWorks Natick, and also improving user experience by multiplexing different wireless interfaces in Telcordia. Currently, his research focuses on novel sensing and management strategies for data center management. In 2012, he received the HIPC Best Paper Award, the IEEE TSPP Grant Award, and the ACM Student Travel Grant Award. In 2013, he received the Rutgers ECE Research Excellence Travel Award, and we are delighted to have Kyung present to us today. Kyung, take it away.
Hello, thank you for the introduction, Sridhar. Yes, my name is Kyung Lee. Yeah, I'm currently last year of PhD student in Rutgers University. So because of that great introduction from Sridhar, I just get started from the introduction. So this is the outline of my presentation. So title is Autonomic Thermal Management in Data Center. So how you manage your data center in thermal aware manner in these days. So actually I introduced the motivations and objectives of this work and what are the contributions what I did in this work, and also the scope of the presentation and then some related works. So because I assume many of you are not aware of data center management, so that I put some emphasis on this introduction, maybe 20 or 25 minutes, and then go in more detail about the solutions, which are thermal management in application environmental layer that I will introduce later, and also thermal management in virtualization and environmental layer. And then I will conclude. So here is the introduction. So there are some observations now these days. So because of this cloud computing and also the big data is now very hot topic in computing society. And then cloud, cloud computing, so actually outsources storage and computing and actually the change of paradigm, computing software as a service or platform as a service and infrastructure as a service, actually which gives lots of opportunities for us to research. So, and also that requires lots of the data centers, huge data centers. And also this big data, so the analyzing human genome and then astronomical data, internet user data for business model and climate simulation. And nowadays, lots of small sensors that feeding in, and then you try to recognize your movement and then your sleep cycle. Actually, they're all generating lots of big data. Actually, that requires the computing power. Actually, that corresponds to the data centers to extract the knowledge. And like the society requires these data centers. And this data center have become a key component of society's IT infrastructure. And then there are some like concerns because of this data center is bigger and bigger. Actually, that consumes lots of energy. And then this is becoming a like energy monster. For example, so in worldwide is a 237 billion kilowatt hour per year, and like 76 billion kilowatts per year in the United States, which is correspond to almost like 2% of energy consumption in the United States. Maybe this 2% is very small number, but this only for the single entity, only the data center consuming 2% is a lot. For example, it's like only the manufacturer in United States is consuming 2%. So maybe you can guess like how much energy is consuming only by this data center. So if you see the this pie chart in this slide, the typical breakup of the data center energy consumption, which is the computation consume like 40%, and then cooling system 35%. So almost like 75% is consumed by computation and cooling system. So here is the thing. So if you can save lots of energy from the computation and also the cooling, actually you can save a lot of energy from data center. So actually this is the start point, actually our research start from. So actually what is thermal awareness, or we mentioned in the title. So this is the, because this energy consumption of cooling is as high as that of like consumption. So we think the understanding of thermal behavior in data center is very important. So if you know how this heat generates and then heat extract in the data center, and then you can manage it well and then save energy in the data center. Even you can detect thermal anomaly and like you can do more about the data center. So give some like example about, say, so we propose this heat imbalance. So which is local unevenness of heat generation and heat extraction. So heat is generated from the CPU and the servers. And also that heat is extracted by the air conditioning system or sometimes the liquid cooling system. And then if we know more about this heat generation and heat extraction, we think we can do a better job in the energy saving. So so in like typical problem in data center could be just negative heat imbalance. So that means, so if you cool more than you generate the heat, then that resulted in the energy inefficient. So because you are overcooling your data center. So on the other side is like if you do like positive heat imbalance, actually that the increase the server temperature so that you are generating hotspots in like data center. Actually, in that result in like server deterioration, and also that decrease the lifetime of the server. So if we know this better, this like heat imbalance, we call it thermal awareness. Then you can maximize the energy efficiency for computation, as for and also for the cooling, and also to minimize the server system failure rates, and also to detect the thermal anomalies. So this is the overview of this work. So our goal is to minimize the total cost of operation. So not only for the computation, we want to save the server changing costs, and we save the computation costs for the electricity, and then you want to also save the cooling cost. So we minimize the data center energy consumption for computation and cooling, and also maximize server lifetime. So our approach is.
I have a question.
Yes.
When you talk about minimizing, energy cost for computation, I'm assuming you're talking about strictly server costs and not costs associated with network appliances, routers, switches, and so on, right?
Yes, actually not the routers and the network appliance. Actually, we are referring to only the servers. Energy consumption for the servers, yeah.
Do you have a sense of how much networking consumes as in that pie chart?
Yeah, this pie chart doesn't say that one, but I have additional slide. Maybe I can just jump into that slide. Actually, I put.
Oh no, we can come to it later if you want. No problem.
Oh yeah. So yeah, instead of doing that, maybe I can explain what is the total cost of ownership later on.
Okay, thank you.
All right, thanks. Thanks for the questions, Reader. And okay. So our approach is a cross-layer thermal-aware management. And our contribution is actually we model this heat imbalance, and then we validate it. And so we propose two solutions, two proactive thermal-aware solutions. One is jointly optimize the cooling system in environmental and application layer that I will explain just next slide. And also we propose the consolidation solution in virtual machine layer. So what is the layered approach? So here is the layered architecture. Now those data centers are the composed of like those layers. This layered architecture was proposed in like 2009 is that part. And so this like different layer acting as like different the functions. So for example, application layer has like workload and the application, the characteristics and the behavior. And then virtual machine layer, because now almost data centers are virtualized, and then they give like virtualization service, and then give the virtual machines. So there's some like virtual machine configurations, and then virtual machine utilization, and then you can get those information from the virtualization layer. And also there's a hardware resource layer, and there's the hardware and the software component of the servers, and also there's the environmental layer that has thermal, hotspot information, and then location and characterization. So using all those information and also the functions, and then actually we can optimize using this cross-layer controller in this figure. So based on this actuator and the sensors. For example, so from the environmental layer, you can get how that server temperature, and then how is the server inlet outlet temperature, and then from the hardware resource layer, you can get what is the CPU utilization rate, and what is the memory utilization rate, and then what is the inlet and outlet server temperatures, those things, and then you can actuate in like different layers. So this is the point of action and then point of the observations. So from this approach, this is the reactive approach. This is previously the proposed. So most of so in this layered architecture, most of this action and observation action loop is like this. So environmental layer, for example, so you directly observe the temperature at the place where we want to control the temperature. And then that feeds the controller, and then you react. And then you change the temperature, and then you control the temperature of your the environment. So, but this approach has like a significant delay for the cooling, because action, observation and action takes time. So this is exactly the same as once you turn on the AC on your car, and then that has the delay to come up with the extra cold air. That is actually like that. So because this delay, so you can actually damage the hardware component before the air conditioning.
Kyung?
So instead, yes.
There's a question that's coming online.
Okay.
Is the delay a function of how much time it takes for the the system to react to the sensors, or is it simply the delay in the amount of time it takes to get the environment back to the desired state?
Yeah, actually, it could be like both of them. So, so because of sensor to react to the air conditioning system in a data center, and then that data feeds back to the system, and then you react it. Actually, that takes a time. So at that I meant in the delay in here. Does that answer your question, or maybe?
No, I have unmuted the individual. I guess you can follow on or send me a further chat. Thank you. Go ahead, Yoon.
All right. So instead of that, the reactive approach, actually we propose this like proactive approach. So by using the information from the other layers, for example, application layer and the virtualization layer or the physical resource layer, and then you can use it beforehand, and then you can optimize it, and then you can preact those actions in the environmental layer. So in this case, delay does not incur, and hence the minimize the energy consumption and also the minimize the risk of damaging the hardware component in data centers. So this is a brief example. So to do that, actually this modeling is required. So to have this estimation of temperature, estimation of the server temperature, so we need some simple modeling to do it. And then we propose this like heat imbalance model, so which is a local unevenness of heat generation extraction. So this heat generation can be from like CPU temperature and the subsystem utilization, which are like a network or memory disk utilization rate. And also this heat extraction rate could be so intake air temperature, mass of the air, so many things. But the problem can be happened because we don't actually know what is the distribution of the workload or heterogeneity of the computing hardware or non-ideal air circulation.
So Kyung, the question is, what exactly are you predicting here?
So actually, so understanding the environment is not easy. So actually, we are projecting so understanding the environment in how it changes in overall in the phenomenon or thermal manifestation, capturing it in this in the data center is kind of hard to do it.
So if I were to paraphrase what you're saying, let me see if I understand this right. The proactive approach works by trying to predict based on workloads that have been run in this data center, across all the layers, the server profiles, the virtualization profiles, etc. It's going to predict, let's say, what the temperature is going to be, say 3 minutes down, down the road. And therefore, if you're accurate, then what you're saying is that you can begin some of the actuators, I guess, trying to cool the system down 3 minutes in advance so that you don't suffer any delay at the time that you require that desired temperature. Is that correct?
Yeah, it's correct. So we propose this proactive instead of reactive. Reactive has delay, so that's like we propose this proactive and plus this layered architecture. So the proactive requires some of the input to predict. So the input is from the other layers, and then we act in like environmental layer. So that way, yeah, we propose like this layered architecture.
I'll back up another tree, but.
Hello?
Yeah, please continue.
Okay, sure. So we need some sensing infrastructure to understand this the environment. So our cyber-physical systems can be employed for monitoring this heat and air circulation in data centers, and then that enables like thermal management. So our phenomenon of the interest is generally characterized by the multiple manifestations. For example, the heat and the air circulation are characterized by the temperature, humidity, and the airflow. So we have equipped with the thermal camera, and also we have like multiple sensors that has the humidity, temperature sensors, and light sensors. And then we collect all this data and then process it and then extract the knowledge out of it, and then to understand and to enable this thermal aware data center management. So we have a couple of observations in a data center. So we have, this is only the toy example I'm making. So we have placed 13 sensors, and we observed how the temperature changes over time. As you can see from this graph, showing the time and then number of servers and the temperature. The temperature look like going high in time. And also because we place all those sensors in vertically, as you see in the left-hand side. So like those are related. So we observed that the internal and external temperature of each server are correlated in time. And also we observed that like those temperatures are correlated in space. Even like the internal, external temperature are correlated each other. So that means actually if you know, so what is the projected temperature outside, and then you can infer what is changing in inside as well. So here are some like a related work. So actually that is the background of how we measure the temperature and then how our sensing infrastructure look like. And then this is a kind of related work what we did before. And so this data center thermal management is changing drastically these days. So before that .com era, if you can see from this graph, so that could be represented as client-server computing and the web page hosting and the financial services and the internet service provider. And then those things, the reliability is the best virtue. They want to keep their servers and then their data in a safest place, and then they want to secure it. And then because this data center is becoming bigger and bigger, and then people need this data center and more, and then this cloud computing era requires more energy efficient, energy savings, and then environmental aware computing. They require that one. So also the research trends also shifted from the reliability and the energy savings and the environmental awareness. So actually I have Google Scholar. So I use the Google Scholar and then count the number of index over the time period from like 1999 to 2013. And then this is how the number of indexes increasing over time. So this is thermal management and the green computing and also cooling optimization and then computing optimization. This topic is growing more attention from the academic and also the industry. So then, like, what are the latest data center design? And also, they have used the metric of the power usage effectiveness, so called it PUE. So this like gigantic data center, for example, the Facebook and the Google have used like this power efficiency, power effectiveness, power usage effectiveness unit. So which is total facility energy divided by total equipment energy. So if this is ideal, so all the energy is consumed by the total equipment. So the ideal number is 1. So if this number is lower, the better. And then Google achieves almost 1.11, and then Facebook data center achieves like 1.05. And then also there's some like debating about like how they calculate this number. But yeah, still, for best practice PUE for the IT sector is like still 1.5. Actually, this implies that a lot of other data centers still using so very low efficiency. So actually, there are opportunities to save energy for most of the IT data centers. So I think I wanna stop here for some time and then having some questions because of kind of introduction phase before I go deep into my work. So if you have any question, yeah, please.
I have a question.
Sure.
So it seems like, at least from the figures so far, this is more about essentially sensing. Is there any work on essentially scheduling jobs within the data center so that the maximum temperature increase is minimized, or the wear on the hardware is reduced?
Yeah, actually, the next section I will explain about like how this scheduling is going on, and then how we optimize this cooling system as well. So yeah, so I can answer those questions later on.
Okay, great.
Thank you.
I had another question. So granted, it's been a couple of years since I worked in data centers. At the time, at least, there was a lot of debate about what should be the right temperature of cooling also, that most data centers were cooled way beyond what is necessary. Is that still the case, or people have figured out what the optimum temperature should be for the data centers?
Oh, I'm sorry, because of voice quality, I cannot like hear every sentence. So can you repeat again, or type in your question in the chat board so that I can understand? I'm sorry.
Can you hear me now?
Yeah. So your voice, quality is better than others, I think.
Okay, so when I was working about 2-3 years ago, most data centers were, at least people felt they were running it too cold, which was not necessary at all. And is it still the case that do people now know what the right temperature should be for not damaging the servers at the same time?
Oh, okay. Oh, yeah. Actually, there's a recommended temperature from the ASHRAE, so Associate of the Air Conditioning in America. And actually, they're suggesting like certain temperature range is good for the data center. Actually, there's a recommended temperature, which is different from what manufacturer is saying about the recommended temperature. So these days is the recommended temperature a little more higher than before. Actually, that has been changed in 2006. Yeah, but actually they're saying, oh, there's a recommended temperature. You keep your hardware temperature in this temperature, and then you are good. Actually, there's a recommended, but you never know what is a recommended, what is a high temperature. Actually, anyway, they put some threshold. Yes. Does it answer your question, or your question is a little different?
No, yeah, that answers my question. Yes.
A related question, Kyung, is the following, which is that even equipment manufacturers, right? I mean, people who manufacture PCs and servers and so on are also designing their equipment to run hot, right? I was reading something, I guess, in that Facebook paper that talked about servers that are designed to run at 55 degrees Celsius, right?
Yeah.
And so that, of course, then dovetails with the question just asked, which means that you perhaps don't need to be cooling things as much because the servers are designed to run very hot.
Yeah. So that is because, like, two things. Yeah, that is because of two things. Because in the high temperature, you can extract the heat better. So because, like, this is like basically kinematic, you can extract better in the high temperature. There's the first thing. And then this is hardware is nicer than before. So that even if you run the data center high temperature, they're saying that, oh, that is fine. Even though you're in the high temperature, your hardware is good to go. But anyway, so my argument is not there. So anyway, you have to control that temperature, even though you can run hot. Yeah, that is fine. You can run it hot.
I see. Does that change any of your dynamics, or is that just simply taken care of in sort of your prediction logic?
Yeah, this is fine. So it is still in my prediction.
Okay.
All right. So I will go on. So this is a proactive like thermal management in application and environment layer. So I already introduced this the layered architecture, and then so this is kind of like pairwise interaction between environmental layer and the application layer. So this is one of my work in 2012 in supercomputing. So you get some information from the application layer and then feed into this environmental layer, and then you predict the temperature, and then you proact. So this goal is to minimize the total cost of operation, and then using the cross-layer thermal area management. And then here is the contribution is, so we do airflow modeling, very simple airflow modeling, and also we do the heat imbalance modeling. And we jointly optimize air conditioner duty cycle and also the fan speed. So here is the simple airflow modeling. This is a hot aisle and cold aisle architecture in typical data center for efficient heat extraction. So the idea is so I have numbered so the airflows 1, 2, 3, 4, 5, 6. Actually, CRAC is the computer room air conditioning unit. Actually, that cools down the air, and this like blue arrow shows the cool air, and this the red dot arrow shows the hot air. So that correct air comes into the rack, and then that goes to the racks, and they extract the heat from the servers, and that goes back to the CRAC, and then cooling it again. So here, this is a simple like this airflow goes once that goes like plenum, which is the flow of like a data center. and then cold air is supplied under the plenum and then returning to the ceiling and then extract the heat from the racks. But this is very hard to estimate it. So mass of the air, that how much air goes to what rack or what server is kind of very hard to estimate it. So actually we propose that we need the sensing infrastructure to measure those things. So this is a heat imbalance model. So how you estimate those things. So actually this proactive approach requires some sort of estimation. So we estimate the heat imbalance, hence we estimate the temperature. So here is this like heat imbalance model is composed of the heat generation model and also this heat extraction model. So this heat generation model has the power of subsystem and also the utilization rate and also specific heat of each subsystems. And then that measure how much heat was generated from your servers. And also you have the heat extraction rate, so mass of the air and the specific heat of the air and so inlet temperature and outlet temperature. So overall you can estimate it. You can estimate the variation in the temperature on your server, so that so that you can predict the variation in temperature in your servers. So based on this prediction, so we can jointly optimize this cooling system. So air conditioner can like extract a more amount of heat. So actually there's two cycles in your air conditioning system. One is the compressor and then the other one is fan. So if you see this equation that shows the energy total is the energy consumed by compressor plus energy consumed by fan. So energy consumed by compressor is based on the compressor cycle and then power of the AC. And then energy consumed by fan is how fast your fan is moving and then power of your reference the fan speed. So based on those equations, so how much so you can say how much total energy cost by this air conditioning unit. So energy consumption for activating the compressor is more than actually activating fans. So actually the compressor consumes like tens of kilowatts, but the fan consumes like kilowatt of the energy. So here is the thing. So we have to find out how much energy consumed by compressor, and then we have to find out how much energy consumed by the fan. So we have formulated this optimization problem. So we have some like given parameters. For example, temperature of recommended temperature, initial temperature, and the AC power, the specific heat of the mass of the air. And also we have some online parameters of heat generation and temperature out and room temperature. And we find the fan speed and then compressor cycle. So we have some the constraints about the heat imbalance causes room temperature change. And we say the room is perfectly insulated, which is not ideal, which is kind of ideal case, but for the simulation we assume that one. So we heat diffraction when the compressor is turned on. So heat extraction when the compressor is turned off. So based on this optimization problem, and then we solve that optimization problem every period. So we have like the period of the cycle of the period, and then we solve that one, and then find out what is the optimal the compressor cycle, and also what is the optimal fan speed at each period. So actually this is a current approach, reactive approach that I explained before. So CRAC react only when the specific event occurs. So there are some like advantages. I told you about this, the delay, and then also there's how you set up the threshold. Yeah, so it depends on how you set up the threshold. Maybe sometimes if you put the threshold too low, right, then maybe you overcool. So if you say too high, maybe high possibility that you may be like the lower cooling, undercooling, I'm sorry. So here's the problem as well. So the controller cannot quantify the heat that needs to be extracted. So that cannot jointly optimize the CRAC fan speed and the air cooled temperature. So our approach is kind of proactive. So we use like those information. What is the application is generating how much heat based on that heat imbalance model. And then this approach is no need to have a like threshold. And then it uses input type and the intensity of the workload being executed. And then this intrinsically predictive. It's based on the control, the causes. Actually, we are measuring the causes, not the effect. So this is a simulation study. So we have employed 3 different types of benchmark. And the first benchmark is the FFTW, and the second one is NAS-SP, and the HPL LinPack. These are distributed computing benchmark. And then as you see in this figure, we put this hot and cold light design. And to compare this reactive approach and proactive approach, we put this reactive approach. The reactive approach is again, so once you detect that the overheating, and then you react. Actually, there's some delay. And then proactive, so you optimize previously, and then just like put it those compressor duty cycle and fan speed, and then you optimize it a priori. So here is the recommended temperature from this like cooling system, which is the 64.4 Fahrenheit and 80.6 Fahrenheit, which is a recommended temperature, which is a shaded, like blue shaded area in this figure. This flow shows the temperature variation in the duty cycle of the air conditioning system, and also the fan speed. So left-hand side, actually we have fixed the fan speed and changed the duty cycle of the air conditioning system. And right-hand side, we have changed the airflow, but fixed the duty cycle of the compressor. And then we clearly see there's some like a risk of overheating and then excessive cooling. Actually, that is actually a waste of energy, or the make the servers in like danger temperature. Because this doesn't not aware of the future heating generation. So this is one of the example of the reactive approach. So based on the application, so based on what application you run on your server, actually this like heat signature or the heat generation and the heat imbalance is different. So here the example shows that the application FFTW generates less amount of heat compared with the HPL LinPack. Also, the right-hand side graph shows that based on the delay, even though it's a react, if you react it fast, and it doesn't overshoot that the blue shaded area, which is our recommended temperature. But if you react late, so this the red bar in the right-hand side shows the 5 seconds of delay, and the green, the blue dotted bar shows the 10 seconds of delay. And then if the delay is higher, and then more possibly you can have the risk of overheating or the excessive cooling. So this compares the reactive approach and the proactive approach. So you can see there's the excessive cooling for the reactive approach. And then the next graph, the proactive approach shows like you are within the recommended temperature. And then they dynamically change this duty cycle at the bottom of the graph. So this is different application, HPL LinPack. Because it generally incurs more. You have any question?
No, I think that was just background noise from someone's unmuted microphone or headset. So please continue, Yoon.
Okay. So this incurs the risk of overheating. So this is overall performance of this work. So this compares to what is a reactive approach and what is a proactive approach, what is the advantage of using the proactive approach. Even the reactive approach, we have like two different approaches in reactive approach. One is return temperature, using the return temperature as a feedback, and the one is internal temperature as a feedback. For example, so if you use the return air temperature for the feedback, that is actually the mixed air for all the servers. And the second case is any of the servers in your data center exceeds some recommended temperature, you react. So here this graph shows that risk, right, as from left hand return air temperature to the internal temperature. Actually the risk has been decreased because you are more conservative reacting. But actually you consume more energy to do that, because you are more conservative and then you have to use more energy to cool down your servers. And then the next is graph show that because you're using proactive, so before you go to risk state, and then actually you decrease the temperature of priority, so you don't risk your servers in dangerous state. And even like this proactive approach, we have studied about using the global control and the local control. So global control means if you have like few fans in your data center, or if you have like multiple fans to cooling down your servers, and then if you have like more servers, and actually you can locally control your environment and cooling down the servers, and then that is more energy efficient. So yeah, local control can even reduces the energy consumption. Actually, that requires actually some sort of a consolidation. I will explain in next section. So the summary is, so data center energy is concerned, and also we propose the cross-layer thermal aware in between application layer and the environmental layer. And the results show that proactive approach is performed better than the reactive approach. So actually, before we go to the next section, I want to have some more questions if you have it.
So can you hear me?
Sure, yes, I can hear you.
Yeah, so I mean, this seems to be a major problem even in large buildings, right?
Yes.
Some parts get really overcooled, and some parts seem you keep pumping in more air. So
correct.
It's not just, this approach can be used even in more generic sense.
Yes, true. Yeah, that's true. But yeah, large building, yes, you can estimate like those heat generation, extraction, and then this can be used for smart building. Yes. But here the thing is, this heat generation in data center is very responsive. I mean, it's kind of like highly predictive. But in a building, maybe yes or maybe not. So actually there are many factors that affect the temperature in a building as well. So because of sunlight and because of number of occupancy in a room, maybe some like air conditioner system in your entire the building. But in a data center is kind of small scale, so that you can predict like those things. But there's some complication because this thermodynamics and then this air fluid dynamic is kind of very hard to estimate it. But if here this data center is kind of actually we scope it down only for the data center, but yes, we can actually extend it for the large building.
Okay.
All right, then I'll go on. Thank you for the question. So second work is still in the layered architecture. And then instead of like environmental layer, application layer, but this is the relation between environmental layer and the virtualization layer. Actually, as Sridhar introduced me, so this is kind of work I best paper over in 2002 in HRTC. So the quick overview is like very similar, but here our contribution is, so we have validated this heat imbalance model in actual server, and also we have used this virtual machine packing, which is proactive thermal aware machine consolidation. So instead of you change the environmental layer, fan speed, and also compressor cycle, actually we do well in the consolidation. So I will explain about what is the benefit of consolidation later. So where you can save energy in data center in general, right? So first one is you can actually better computing resource utilization. So then if you turn off the unused servers after you consolidate it, and then you can save energy. So this is very intuitive, right? So if you consolidate some of the servers, some of the workload, or some of the virtual machines in other servers, and then you can turn off other, so idle servers, and then you can save energy. And the second thing is you can improve the CRAC system performance. So actually this is related to why we have to run the data center in high temperature. So this, the coefficient of a performance increase when you run data center in high temperature. Right? So you don't need to work a lot in high temperature to extract the same amount of heat. So this is similar to the utilized servers that are in better cooled area in data center. And then if you can efficiently extract the heat in better cooled area, so you can save energy. And the third thing, and so because if you can avoid certain places too hot, then actually you can increase the lifetime of your servers, and then you can save energy. So this is a cross-layer like thermal air management. So we have uses some of the information from the application layer. So there's an application request, and then that feeds into our heat imbalance model. And then actually we do in virtualization layer, we do some virtual machine provisioning. That is where we have to place those virtual machines, and then where we have to consolidate it, and then where so how to manage it. So and then using some of the information from the hardware resource layer, and then we consolidate those virtual machines. So that actually requires the information from our external sensing infrastructure. So I just recap this our heat imbalance model. So this is generation and extraction, and we can estimate the variation in temperature. Then how we do it? Actually, we validate that model in this work. So first of all, we estimate to measure the power. So how much power it consumes in 25% CPU utilization rate, and then 50%, and then 75%, and then 100%. How much it consumes the power. And also the same thing in 25%, 50%, 75%, and 100%. We measure the temperature, and then how that changes. And then we have actually validated this heat imbalance model. And then so we compare with estimated CPU temperature and the real temperature, and then it doesn't really differ each other. So we can use our heat imbalance model. And how we can use this, how we save energy then, so based on the temperature. And then how we save energy. So we observe that if you increase the CPU utilization rate in the x-axis, and then power is like this behavior logarithm. Right? So if your CPU utilization is 0, that means your server is idle, and then you are still using power of like 80 watts, almost 80 watts. Right? But if you utilize more, and then that behaves logarithm, that means if you consolidate more, and then that the increment of the power is like less than if you're using like the 0 or 10% of CPU utilization rate. So that means if you do consolidation, so lower energy consumption, and also for the temperature, if you do consolidate and then if you increase temperature less. So using those things, so we also formulate this optimization problem. So given we have some parameters of these servers and the set of VMs and the period of optimization, and then actually we want to find the associated metrics. So where we have to put that the virtual machines. So we have some constraints. So virtual machines are allocated in one server, and also there's some restriction for the temperature as well. And then this is solution. Actually, this formulates as a variable size bin packing problem, a multi-dimensional bin packing problem. So now is a bin size is servers and objectives, and then now the input is not only the application, but this is a virtual machines. For example, you request a virtual machine in Amazon EC2. Actually, you have to request so number of CPUs you are using, and also memory and network bandwidth. Right. So that is actually multiple dimension, and then you have to pack those the multi-dimension objectives to the bin, which is a server, which is a finite the dimension. Right. So this comes into variable size of multi-dimensional bin packing problem. Because this is an NPR problem, so actually we have a heuristic heuristic solution. I don't want to go detail about the solution itself, so you can always refer to my paper. But the idea is we sort it based on the decreasing order of their deadlines, and also because that is desirable to pack longer duration virtual machine together, so that smaller duration of VMs can be switched off once it's done. So this is the basic idea, but there's more in that. And then also we have used that migration techniques. So when the energy saving is outweigh the overhead of the migration, which could be the migration delay. Yeah, there could be some more, but majorly it's migration delay, and then you can migrate it. Right? So this example shows what is the condition that you can actually migrate the virtual machine. So yeah, this is an experimental setup, and then we have equipped with this sensing infrastructure, and then this is the airflow on the left-hand side, and then we do the federated data center scenario with the University of Florida, and then we have a simulation scenario of. So we have used virtual machines, and which runs the workload of sysbench and the tau bench. We assume that sysbench is CPU intensive, and the tau bench is CPU plus memory intensive workload. And then we have for the simulation study, we have used the integrated cluster workload traces. So we have measured the energy consumption and also the thermal violation duration. So our idea here is we try to minimize energy consumption, but not violating the server or the overcooling the server. So this performance shows that our virtual machine VMAT performs the best, and we have other competing algorithms. So this is kind of scheduling. So there's a round robin, and then best fit decreasing, and then best fit decreasing, and then first fit decreasing reactive. So you want to compare the reactive as well, and then best fit decreasing reactive, and then cool job. So we can clearly see the round robin in CJs a lot, because that blindly just plays the workload all the servers. The round robin or CJ. Cool job is most coolest place you put it over there. And in this case, round robin or cool job doesn't incur significant the thermal violation at the next graph. But also VMAP is energy consumption is kind of minimum, and also it doesn't actually incur any thermal violation. So that means you are more intelligent actually, because we are we predict the temperature increment beforehand, so that you can just optimize it before you place those the virtual machine in some place. So that's why we don't incur any the thermal violation. The second graph shows the COP. So this is the graph from like Rutgers University in Florida. And then because the Florida server is running like higher temperature, so that so you can be more efficient for the cooling energy consumption. And then the next graph shows that if you increase like higher temperature, and then thermal violation increases. But like our solution, which is DMAP, doesn't incur that much. So next, the performance evaluation section shows that, so we have like this optimization period, and then how that impacts. So for example, if the delta, which is the period of the optimization, is big, and then complexity increases. Yeah.
Just a quick interrupt, since we are coming up on 1 o'clock, and there may be people wanting to leave. Folks, for those of you that need to leave promptly at 1, please do fill out the seminar survey. That's very useful for me in tuning the seminar offering. And for those of you that can continue to stay, I think Kyung is going to stay on for a little bit after. Thank you. Go ahead, Kyung.
All right. So actually, this is the last slide. So if this is delta is a window of the optimization is big and the complexity increases. But if the delta is small, the complexity decreases, but the solution is less efficient because there are fewer virtual machine requests are optimized. So yeah, so this all happens. So this is concludes actually my the presentation. So this is summary. So we propose this is cross-layer thermal area management. And then that aware the thermal, so temperature, and then we validate this heat imbalance model. And then we propose this proactive thermal aware virtual machine consolidation. So yeah, this concludes my presentation. But I want to mention this one. This data centers now is virtualized. So actually, this virtualization gives you opportunities or some lots of problems maybe. So because your actual server is not the server you are running on, right? So actually, if you buy one the virtual machines or the server, maybe you think it's a server, but that is not the actual hardware server. Actually, there is a virtual machine running on the actual hardware. So actually, that can be in just one static server, but that can be moved anywhere. Maybe later, sometime, maybe that the virtual machine running on the other side of the earth sometimes, and then that go back and forth. So energy consumption and also this like data center in the virtualization environment is a kind of like significant concern these days. And then so people try to optimize. So how to minimize it, and then how to guarantee the reliability, and also while you are ensuring the energy efficiency. So my scope of my work is in that. So virtualization and also minimize energy consumption. Yes. So yeah, I hope like you enjoy my the presentation. If there's some the mistake I made, please forgive me. And so yeah. This concludes my presentation. If you have any question, you can ask.
Thanks, Yoon. Folks, any questions, please send them to me by chat. I think some of you are muted because I think there was a lot of sound. But send me the questions via chat. Others of you are unmuted. Please ask the question, and we'll wait for a couple of minutes. Otherwise, I'll ask a couple that I have.
So I had a question. Doesn't VMware already provide some sort of optimization to move the servers around today?
Okay, so why you have to move the? So actually, there are other. So I just mentioned about like moving the virtual machine the other side of the earth, right? So actually, the cost of electricity, right? There is some work about the cost of the electricity and where you have to run the server. So that means. So while you're running the servers, maybe during the night, during the daytime, and then the other side of the earth is the night. So the electricity cost it's much less during the night because not many of people using the electricity during the night. So that is like a simple, even the daytime, the electricity costs like up and down. So some researchers suggested, so maybe if you run the server the other side of the earth during the night, and then maybe you can achieve like, better efficiency. So you don't need to pay a lot of cost for running your service. So that's why I mentioned about moving the virtual machine here and there. Also, this like virtual machine migration can be used for for the consolidation that I mentioned in here. So if you consolidate it better, and then you have to, if you can extract the heat better in certain area, and also you can turn down other servers, and then you can have some more efficient like energy conserving.
I think the question was actually a little bit more about, does VMware already provide VM migration for energy efficiency, if I got that right?
Yes. So not the energy efficiency per se. So so VM provides that that service, yes. So you can move the things during the night and during the daytime. Actually, they're what they're saying is that if you consolidate more things during the night, and then you can save energy. Yes. And then actually what I'm doing is more than that. So if you do consolidate better, not only just during the day and night, if you consolidate some better place for the cooling as well, and then you can achieve more. You can like save more energy.
So related question to that I have, while others might ponder their questions, it relates to, I guess, you're quite right that you provide sort of the underlying technology that, or algorithms that perhaps VMware or other, technology providers can use. So related to that, have you, I guess the first question is, what's the scale at which you've done your measurements? How many servers? Give us a sense of, you talked about Florida and Rutgers. Are these running tens of servers, hundreds of servers, thousands of servers? I mean, give us a sense of the scale.
Oh, okay. So we have used here, we have used the 3 enclosures. 3 enclosures have almost 40, so 16 multiplied by 3 is 48 blades. So 48 blades.
Sorry, can you repeat that, Yuntu? How many blades?
Yeah. So we have used like 3 enclosures. Enclosures have like blades. So this is like, so one blade is kind of server.
Okay.
So this the latest, the distributed computing design is a little bit different from like traditional server. So one server is a one blade.
Okay.
And we have used like 48 blade, for example. Yeah.
Okay, so 48 blades in Rutgers and 48 in Florida?
Yes.
Okay, okay.
More or less, yes.
So how applicable do you look at, do you believe that the large data center providers, both at the cloud level, the Amazons and the Facebooks, etc., how applicable do you believe that your research would be to their particular environment? In particular, I see 2 things. One is the scale at which they operate. That's one, The second is, from your metrics, you were sort of looking at blades that ran particular workloads. As I understand it, of course, there are probably some key applications that run at Facebook or Amazon, etc. But I'd imagine that there is a lot more diversity to workloads at those data centers. So how does that affect, affect your study?
Yeah, actually, this is thermal footprint. So heat generation of like specific server is all different. So that so based on the server and so based on the computer architecture, and then those signature might be different. So that like first one is that you have to profile well, and the profiling is very important. So you have to profile the thermal imbalance, and then you can apply the techniques. So so for that, so to answer your the scalability issue, so if you apply this technique for Amazon or the Facebook and other data centers, and how to, yes, this is a problem. So we have an idea of using like thermal camera. So because like those the thermal the sensors, and then you have to put like those sensors in each individual the servers and the blade, and then you measure it and you profile it, and then that is not scalable. Yes. So then we try to use the thermal camera to have a picture of how that heat map changes over time, instead of you measure like scalar sensor and then measure it. So based on like those thermal figures, that you can cover like tens of rack, right? Not only like just 3 enclosures, but you can cover maybe the tens, maybe hundreds of like racks maybe. So yeah, it depends on the size of the angle and everything. But yeah, so based on that one, actually, we propose solution that we can overcome that scalability issue.
Is that covered in some paper that you've talked about? Is there a paper that you can that addresses the scalability? That I'd be interested in reading that.
Yes, we have a paper in 2010. ComNet and IEEE. Yes.
Okay, I'll talk to you offline about that.
Okay, sure. Yeah. Thank you for the question, though. Yeah.
Any other
one more
questions?
question. Okay. So it seems like, at least from the figures, the best results always occur by concentrating workloads after they've been profiled. Are there any applications where the best result is actually to distribute the workloads further instead of concentrating?
I'm sorry, your voice is not clear for me. I'm sorry, can you explain again?
Sure, okay. So it seems that you always get better results by concentrating the workloads into
Consolidation
fewer servers.
workload. Yeah.
Are there any situations or any workloads where it's actually better to distribute them further?
Okay. Yes, I think your question is, so there's some workload is not consolidating, but like you have to distribute the workload. Mm-hmm. Is it right, your question?
Yes.
And then how our solution deal with that kind of situation.
Mm-hmm.
So yeah, actually we have studied like based on like different types of workload because we are originated from the distributed computing. So we try to use like the distributed the workload as well, right? So anyway, that essence of that distributed computing. So you have to parallelize like those workloads here and there, and then you can maximize the make span, or you can maximize the running time. Right? But for our specific cases, the virtual machine allocation, we didn't actually concern that kind of cases. So actually, we only focus on like consolidation, not distribution.
Mm-hmm. Okay.
But yeah, we have studied about different applications. For example, we try to use this technique for not only this distributed computing workload, but we try to use this one for the web application. So actually that web application and that like pattern and the heat pattern or the CPU utilization pattern is quite different from the distributed workload. So that, yeah, you might have to like profile this again about like that heat distribution.
Okay, thank you.
All right, thank you for the question.
Any other questions? I guess hearing none, I guess let's do the following. Yoon, I have your coordinates, so folks, if you guys have additional questions, etc., please feel free to reach out to Yoon directly, or else forward me your questions, and I'm happy to connect you or forward the questions on to Yoon. As I said before, the slides and the recordings will be available shortly. The slides will be available almost immediately, but it takes a little while for me to get the video encoded and uploaded into YouTube, probably in the next hour or so. Let's see. With that, I think, and do please fill out the survey. That helps me and the speakers, etc., improve our seminar program as we go forward. I guess with that, we have this tradition, Yoon, where we all, because we're all in different locations, throughout the country and the world, let's actually all unmute our microphones, etc., and give Yoon a warm virtual applause. So let's do that right now. So,
thank you.
Yeah, thank you, Yun, for a good thought-provoking presentation, and we'll see you all shortly. The seminar for the month of May is not scheduled. Please await an announcement for when I'm able to schedule that. Thank you so much, and see you all next month.
Thank you, Sridhar. Bye.